So welcome, and again, just to echo Hayley's comments, great to see everyone. Many thanks for taking the time to come here. I always say to Hayley that we do great science. In fact, I told the board actually last week we do great science, and we do great science, and hopefully we'll showcase that today in the presentations and the posters. I'm going to talk a little bit about directed biology, a little bit of what it is, and how we've developed a platform at Domainex. Oh, blimey. Is that looking all right on the screen? Yeah. Okay, good. So here's a hypothetical project. We've got a hit, for example, from a fragment screen, and we want to explore the AMI vector. And basically, we want to explore a large chemical and property space. We want to use all the available tools to ensure that the right compounds are made, and we want to be efficient with our time and resources. Now, if we look at the classic design, make, test cycle, and we look at a benchmark of, say, 1,000 compounds, well, clearly compound design, we can certainly design over 1,000 compounds a week. Using plate-based chemistry, we can actually synthesize over 1,000 compounds a week, and clearly biology can test over 1,000 compounds per week. The real rate-limiting step is compound purification. And even if that 30 is an underestimation, it's well known and recognized that in the conventional chemistry design, make, test cycle, that purification is a bottleneck. So what directed biology does is we remove that purification bottleneck. We carefully design directed biology compatibility experiments, and basically we cherry pick the top hits for compound resynthesis. So in a directed biology-enabled drug discovery program, expensive hit resynthesis and purification efforts are really only invested in compounds with the right measured properties. And in some ways it complements the traditional round bottom flash synthesis. And we advocate that where the biological assay, for example, is not compatible with directed biology, or there isn't a well-defined vector for analogs to be defined, or you're looking at fewer data points, or you're asking a specific scientific hypothesis. So looking at the D2B evolution, so sort of 2020, there's, in my view, a seminal paper around about 2014. And what they showed was that using SPR, a very good agreement in KD off rates between unpurified reaction mixtures versus purified compounds. And we know that KD off rates is a measure of compound potency. So using SPR, unpurified reaction mixtures, you can get a feel for the potency of your compounds. Some early adopters of directed biology were the covalent discovery cohort. And of course, here they're using a mass spec based platform. And mass spec's great for looking at unpurified reaction mixtures, because here you're looking purely at the protein and the interaction of the covalent inhibitor. But in my view, it was really the early 20s and the PROTAC revolution that really raised the profile of directed biology. And many large pharma, GSK, AZ, Janssen, they published papers demonstrating the benefits of directed biology with regards to accelerating PROTAC synthesis and certainly hit finding activities. But in my view, directed biology is beyond PROTACs and should actually be used as mainstream drug discovery. And a nice couple of papers that were published, certainly one last year and one this year, successful hit finding in molecular glue space, where clearly it's probably a numbers game. And then Merck published a nice paper in 2024 looking at rapid HiDAC2 affinity ranking using crude reaction mixtures. So what's the advantages of directed biology? Well, clearly it's cost effective versus conventional synthesis. You get a high speed cycle time. For a one-step directed biology, we can make 1,000 compounds in 10 days. That's the synthesis and the profiling. Looking at traditional synthesis, purification, testing of 1,000 compounds, 1 FTE around about 6 months. The other advantage of directed biology, of course, is favourable regarding environmental footprint. You get reduced reagent solvent consumption. So to make 1,000 compounds for directed biology, we require about 75 mg of a scaffold. Whereas for traditional synthesis, looking around about 10 grams to make 1,000 compounds. So quite a large difference. Oops, has it gone off? Oh, it's gone off mine. Oops, sorry about that. Not catching up. Okay. Sorry about that. Okay. This is Domainex's validated directed biology chemistry platform. So we've got a lot of experience in the classic one-step amide coupling reaction. We've taken a step further. We can now do what we call a 3-in-1 reaction. So we take an amine, do an amide coupling, remove the protecting group, do a second amide coupling, all in the same well. And in fact, we think this is probably pushing the envelope as it currently stands. We've used this reaction in 2 independent hit-finding campaigns and found novel inhibitors. The reaction below is a one-pot azide formation copper click reaction. So Neil London published a great paper a couple of years ago where he took a commercially available azide library and did a copper click with a POI alkyne to form triazoles and basically screened those unpurified in cell-based assays. The challenges of the azide library, the azide commercial library, is one, diversity, and one is probably cost. What we found is if you take primary amines, you can do an azide transfer in situ, and then the same reaction will add the POI alkyne under click conditions, and you get a very nice conversion to the triazole. And like most CROs, we have a partial PROTAC toolbox. We have a subset of partial PROTACs. I've got a linker with a terminal amine on the end of it. And so we've taken those primary amines, converted it to the triazole in situ, and reacted with the POI alkyne to give you basically PROTACs with a triazole linker. And in fact, we just applied this particular reaction to a client and obtained some novel PROTAC inhibitors. We've also done some Buchwald-Hartwell cross-couplings, photoredox decarboxylation, very good performing sp2, sp3 couplings, Suzuki cross-coupling, redox SN2, we've also applied that to a client project and got some novel hits, and then finally SNR. It's a quite diverse set of chemistry, all done in 384 well plates. Wrong way. So a typical directed biology workflow. Step 1 is really assay development. Here we establish a biological assay, whether it be GCI, which is like SPR, a spectral shift, a high bit, cell type to glow. Step 2 is the key step. This is what we call a directed biology compatibility study. Here we demonstrate that really project agnostic crude reaction mixtures show no effect in the biological assay. In other words, you look at an amide, for example, an amide reaction, we might take something like pyrrolidine and benzoic acid under, say, 6 different amide coupling reactions, a couple of bases, different solvents. We then run those particular crude reaction mixtures in the particular biological assay of choice to make sure that biological assay still performs to a high quality. And then we take those particular crude reaction mixtures and then spike in a positive control to make sure that positive control behaves as it would as a pure control. Step 3 is reaction optimization. Here we optimize the chemistry to increase the probability of success. Step 4 is the D2B synthesis. We carry out the reactions, analyze the crude reaction mixtures using UPL-CMS. And step 5 is the hit resynthesis, where obtained hits, we then look to resynthesize and validate the assay results. This is our directed biology compatibility matrix. So again, on the top row, you've got the validated reactions. The first row going down is the actual biological assays we've profiled the reaction mixtures in. So you can see that they are all compatible at the concentrations tested. And then just to give you a bit more in depth on those sort of assays. So for the bioassays, we use a high bit cell line with a positive PROTAC control. Unfortunately, I can't disclose that due to confidentiality. For the spectral shift, we use a BDR3, BD2 labeled using NTA dye with a PROTAC MZ1 as the control. And then for GCI, we use BDR4 and protein binding, and again with the MZ1 as a positive control. And this is the sort of typical output we get. So here's, again, a classic agnostic reaction, pyrrolidine reacting with benzoic acid under an amide reaction conditions. And the first plot on the left is basically the running the crude reaction mixture in a high-bit assay in the absence of any positive control. And again, we see no effect on cell viability, and gladly we don't see any degradation. We then add in the positive control, and then we see a nice degradation, and again, we don't see any effect on cell viability. That's a really nice result to see. In terms of reaction optimization, again, the desired transformation is screened in a 24-well plate to find those optimal conditions. We can use multiple building blocks. So again, for a typical amide coupling design here, we've got 6 different amide coupling agents, a couple of solvents, a couple of bases. That's 24 reactions in parallel. And then we use automated LCMS to analyze the plates. This is an in-house Python script to automate the interpretation of the LCMS data. It's routinely used across the Domainex high throughput experimentation platform. The key advantages are that it removes that human interpretation, and we can run a 384 well plate in a single overnight run. And on the top right is a typical heat map of a reaction, and below is a typical chromatogram. And then in terms of obtaining the assay data resynthesis, again, we resynthesize hits using the same plate-based conditions, but on a much larger scale. We then purify, looking to around about 20-30 mgs, really to support further downstream profiling. What about screening unpurified reaction mixtures outside the biological domain? So AZ in 2023 reported excellent chrome-log-D and EPSA correlations between unpurified amide reaction mixtures and pure compounds. And Domainex repeated this exercise with a much larger amide data set, and we actually observed similar excellent correlations. And for me, actually getting hold of chrome-log-D and EPSA data actually is very useful in drug discovery. So AZ published a great paper this year where they took their internal PROTAC collection, added in some commercial PROTACs, and then ran that whole collection of compounds through what I call normal small molecule ADME assays. And what they found is that certain assays have a chrome-log-D threshold. And basically, above that threshold, there were concerns over the interpretation and the robustness of the assay data. And therefore, a red flag was put on that data. So for example, we look at fraction unbound. Anything above 3.5 would be a red flag. Turning to EPSA and TPSA, obviously, EPSA is the measured polar surface area, whereas TPSA is the calculated surface area. And in fact, if you take the ratio of EPSA over TPSA, that ratio is less than or equal to 0.8. It's suggestive of polarity reduction and molecular shielding or static or dynamic intermolecular hydrogen bonds. And that's a very useful information to feed into drug design. And then if you combine chrome-log-D with EPSA and then you bring to the table heavy atom count, that can generate a metric called balanced pyrimidine index, which is a BMS metric. And that's highly predictive of Kappa-2 permeability and PGP efflux. And in fact, what BMS found was a very strong correlation of KPUU to and CNS partition to balanced pyrimidine index. What about D2 ADME? Is that a new frontier? So Merck reported an excellent correlation of human microsomal unbound intrinsic clearance between crude reaction samples and final purified products. And this is for the amide and Zucchi reactions. Domainex, we actually approached this slightly differently. We focused on the amide reaction. We used probe compounds for the 7 major CYPs. We then measured the intrinsic clearance for the probe compounds in the absence and presence of the amide coupling reaction mixture. And what we found was there's no impact on the baseline intrinsic clearance of the CYP probes. And in fact, we've repeated this exercise with the Zucchi reaction. And again, we find no effect, in line with the Merck observations. So to summarize, directed biology can be a very powerful tool in the MedChem toolbox to accelerate hit ID and hit expansion. It requires reduced material needs. It concentrates resources on the most promising compounds. And at Domainex, we follow a very stringent directed biology workflow. And in fact, the compatibility study represents a real go, no gate. Outside the biological domain, directed biology can generate high-quality decision-making chrome-log-D and EPSA data, and is D2 ADME a new frontier? Well, time will tell. Before I hand over to Jim, just to say that we have some posters that capture and showcase directed biology in fragment expansion, in a covalent hit finding situation, and also use of our partial PROTAC toolbox. So I'm now going to hand over to Jim.